Looks like S and R. How'd we do? Did I get them right?
Yes.
Questions about those two? Questions?
Why would the second, why would the number 2 be higher than number 3? Because I thought that since it has that.
This carbon here.
No, no, the other one. On A.
Carbon here.
Yeah, why would?
Nitrogen beats carbon and carbon. Nitrogen's 1. Carbon or carbon, which wins?
The one
You got to look at what's attached to it.
on top,
What's attached to this carbon?
that nitrogen.
Nitrogen, H and H. Connected to the carbon is nitrogen, H and H. What's connected to this carbon?
Carbon.
Carbon, carbon, and carbon. Carbon, carbon, and carbon. Right here, you look at the first. Nitrogen beats carbon, so this is your winner. You list these. Basically, it's not a collection of these. You don't sum them up. It's just this has the highest priority connected to it. That's 2. So it looks like it's clockwise, but the undrawn H, low priority group,
It's forward.
is forward. The forward group is forward, so we reverse that to counterclockwise S. What does S mean? I think these are Latin. Sinister. I believe sinister, left. See, left-handed people were sinister. Okay. I don't know. I think that's right. R, I think, means rectus, or right. Okay. Because with S, aren't you, counterclockwise is actually left, or where clockwise you're turning the clock down to the right. That has to do with the question on eyes, ocular, OD on the warm-up page. Yeah, okay. Everybody know eyes, OD, and OS? Yep. Okay. There we go. Other questions? It looks like an 80% EE of L. That's what rotates. You get 80% of max. Max was 10. Be negative 8.0. No calculator required. How we doing? No? Here's your Fisher projection, and it's 3O. The fluorine and chlorine high priority groups are on opposite side of the Fisher projection, with the methyl and ethyl joined at the top. Fluorine on the left, chlorine on the right. How do we do? Questions? 3O?
Did the other way around. I put my feet at the other side, but it's technically the same thing.
Technically the same thing.
Just put my feet at the other side.
Where's your answer? Well, that's not technically the same thing. You got the 3O part right, but your Fisher projection is the enantiomer of this. So it would not be counting correct. You drew the mirror image here. Yes, the mirror image of this of 3O is 3O. But so you have gotten that correct because I didn't. What you have drawn, what you drew is 3O, but what you have drawn is the enantiomer. And your feet in the air, is that right?
Yes, sir.
You're upside down. All right, you have the enantiomer. Which one is chiral? It ought to be this one, because the other 3 are not. I looked at those kind of first. I could have looked at this one, but this, what is it? I drew this in the Fisher, and I easily saw that you had plane symmetry here. We'll look at some of these, yeah, how we do on this one? We haven't quite looked at these yet. Question?
On number 3, you wouldn't care if you wrote like ethyl instead of drawing the
I would probably prefer you to draw it out. I mean, I know I do put ME, but I'm just sort of putting it on the end there. As you get bigger, I mean, you can if you know what you're doing, but I prefer you draw it out so I can see that you know what you're doing. Otherwise, before you know it, we're just never drawing structure. Okay, how do we do on this number 4? Question?
In the second structure, are the
Below.
in the second structure are the carbons not chiral attached to the Cl and F?
Here?
Yes.
Yeah, that's not even a chiral carbon. Okay, you can put your pencils down, I'll blow your mind. You can actually have a chiral compound that doesn't even have chiral carbons. We haven't covered anything like that, that's an exception. But you can. Due to restricted rotation or some other ways, those are, okay. So yeah, it doesn't even have chiral carbons. For us, that pretty much is going to make, now, did anybody who was here 30 minutes ago redraw this maybe like this? The chlorine, the 2 halogens are what? Cis or trans?
Trans.
Trans, and they're 1,4. So you can put one here, and then put one here. Yeah? Easier to see, Waldo. Now, right down the middle. Half a chlorine going back, mirroring half a chlorine going back, half a chlorine, okay? I kind of see it here, and maybe I'm just already seeing this in my head. We'll do a couple of those. That's where we need to pick up at today. We discussed it this morning during office hours. That one by Jonah Fisher and so I said, well, this must be it. Then I kind of checked myself because I said, hey, if this is, hold on. One of the following compounds is chiral.
I thought that was R.
One of the following compounds is chiral. Oh no, if this is RS, that's meso, and it's not chiral.
That's RR, isn't it?
Did I just jump the gun and assume that? I may have, this is grown. I see a plane of symmetry here. Is this the answer? It can't be RS. If that's RS, that's meso because you got the same stuff connected over here as over here. And if it's mirroring, that's a plane of symmetry. Is that right?
No.
1, 2, 3, R. 1. Yeah, I got this wrong. I just jumped the gun here and got it wrong. That's 1. Carbon with bromine would be 2. Carbon with carbon would be 3. H in the back, so this is also R. Okay. I was trying to check myself, but I just did it too quick. RR, and since it's RR, you know it's not a plane of symmetry. But the plane of symmetry would have to be RS, correct? Okay, so I got that wrong. Possible, you do have the same things over here, carbon with bromine, carbon with ethyl, but if they're not mirroring because one is projected one way, one's the other. If you want to draw it out in the Fisher, yeah.
So for the chlorine and chlorine one you drew, when the in the structure on the paper, when the second half is like coming towards us, would we just rotate it to go flat and that would automatically push the other two out?
This is just a different way to draw a 6-membered ring. First off, they're all bad because we know the 6-membered ring is actually in a chair combination. So this is where it's drawn instead of just sort of flat, it's sort of turned, and like this is coming out at you. Okay? So that's just plain flat up there. Here it's like this. Now, see here you put the groups forward or back. But if you draw the ring like this, you can put the groups up or down. And see, that's how it allows you to put these groups up or down, envisioning the ring being like this. Well, if you can't see the plane of symmetry here, we'll do some more as practice. You can just redraw these in a more of a like that, and that's what I did there.
Right.
Now do you see the plane of symmetry a little easier? Half the chlorine going back, half the chlorine coming forward. Yeah. Same thing here. I can sort of see the plane of symmetry through there. I got a half, this is really cutting right through the chlorine. And you got this, that, and half the chlorine. If you redraw that the same way, you'll see, we do it real quick. That's a 5-membered ring. I'll draw it with the point at the bottom. Chlorine here, you can do an enantiomer, but let's draw it down. How about back? If that's back, the two bromines are up, so they're here, but they're like this. Okay, there's another way to draw the compound. Now do you see the plane of symmetry? I mean, it's right through there, half the chlorine. Where here, it's hard for me to draw through here and through the chlorine because it's turned and everything. Yeah.
For the Fisher projection on the far right, does it matter if you put the methyl or the two ethyls?
This here?
Does it matter if the two ethyls are on the going away part of it rather than the chlorines? Can you put those on the ends? Does it matter?
I put these on the end because that's how I originally saw it. With the chlorine going away, now the ground's here, so this is the top chlorine. With the top chlorine going away, this ethyl is on,
Yeah. But
right.
can you
So I
do
drew it like this.
You can do it the other way though, right?
Well, to me it's, so you said with the ethyl going away, how are you looking at this? I don't get how you're looking at it.
Yeah.
That's not how I've been showing you in class. How are you looking at it? Now, you're not saying you drew this and then rotated it. But you could, but what's the point? Because you can see it here. I didn't ask you to draw it with the ethyls at top or bottom. I mean, I can see the plane of symmetry here without rotating. I don't quite see how you went straight from here and had the ethyl back. So that's not the way I've been doing it in class. If it works for you, fine. So, but did it work for you? You're saying.
I got the same thing, just the chlorines were.
Okay, so you got, if you move this up and move this down, you can put the ethyls at top and bottom. If that ethyl moves up, the chlorine's over here. If this ethyl moves down, the chlorine's also over here. Yeah, see, there's the plane of symmetry. It's still there. You got this? Okay. I'm not sure how you did it, but if it works for you. I've been showing you to look at the things in the plane. I look at those as going away. And the things that are dashed in bold, I do like this. That's the way I've been showing. Yeah? Any other comments, questions, accusations?
If I'm doing these just by, like, I found out that was RR, and so I knew it was chiral, and then I checked myself by finding out that was RS just by, I didn't go to a Fisher. Is that going to mess me up eventually? Or is that method okay?
You're kind of using some tricky methods. That works, I think. Yeah. If you recognize.
So I can trust the...
A meso is
magic?
always going to be RS, or mirrored. If you got 4 chiral carbons and one's R and one's R, for this to be a mirror, this has to be SS.
Yeah.
We haven't done one with 4 chiral carbons, but it
Okay.
works the same.
I just want to make sure that's not going to...
I don't see anything that's
bite
going to
me.
mess you up. You're kind of using a trick. Okay. There's a variety of tricks. I can't just tell them all to you because we don't have enough time, and then you get confused. But if you can pick up on them and use them, yes. If that works for you, stick with it. I tell you the systematic approach that I recommend, and then I try to and tell you some other things. Okay, 16 down here, is that right? 2 to the 4? I think that's 16. I didn't bring my calculator. How we do on that one? Everybody get 16? Because you had 3 chiral carbons and 1 stereogenic alkene. Each of these starred positions has 2 possible configurations. R and S for the carbons, E or Z for the alkene. Where's this string? Correct? Question?
I thought carbons that were attached to a ring couldn't be stereogenic.
Carbons attached to rings?
It's,
No. No, the only thing is this alkene's not stereogenic because it's on a 6-membered ring.
oh, okay.
If we're making a 6-membered ring here, okay? Well, let's just 4-membered ring. Well, if I'm like this, I can't participate in this ring. I have to be cis. 6-membered ring also. If the rings get huge, then you can start having death. Now you might wonder, well, how big? Well, I mean, I'm not going to give you something and say, no, that's stereogenic. What you should know is that a pi bond in a 6-membered ring is not stereogenic. Or smaller. It cannot be, see right here, this is cis, or Z. These bonds cannot be trans and still have a 6-membered ring. It's not geometrically possible. So there's no alternative there. You're never going to have a situation where these are drawn trans, so it's not stereogenic. Other questions here? Looks good? Yeah? Okay, one at the bottom. All right, the one at the bottom we really haven't touched on yet, but here you go. Here's the first time to do. Anybody get the answer? Half of it is really easy, because half of it's regiochemistry, the other half stereochemistry. For example, first off, what are we making here with bromine and water? A little memorization.
Halohydride. Hydrate, yeah.
A halohydride, right? I mean, you got that on your note cards, right? It gets you going. Okay, halohydride. That means I'm going to put a bromine on one carbon of the alkene and an OH on the other. Which carbon is the OH going to end up bonded to? Left or right? On the right. Why? Because bromonium ion, and then the water attacks which carbon? The one where the cation would be. That's more substituted. Well, it's not really a cation. OH is going to be here. So the OH is going to be bonded to the carbon with the isopropyl. Well, it ain't this one, because the OH ain't bonded to the carbon with the isopropyl, so I'll mark that one out. It ain't that one. The OH ain't bonded to the one with the isopropyl, so I'll mark that one out. OH bond, here's your two choices, really. Now we're looking at stereochemistry. Are you going to end up with, as drawn, 3O? Or will you get, as drawn, erythro? Does it give both? If it gives both, then that's what your question is invalid. It only gives one. Which one does it give? Well, obviously it's one on the right. If I get this correct, other than just guessing? Did you get it right?
Because I had C, and then I don't know why I changed it.
Uh-huh.
I really don't.
Okay, a lot of students say it's C because the bromine and OH are opposite. And they're like, well, the bromonium water comes in backside. Yeah, but we can rotate things. You have free rotation. No, this is it. Then students get confused. Well, why are they on the same side? I thought it was anti. Well, I did the mechanism over here. Okay, I'll say this here, and then I'll maybe repeat it when we get over to our handout. It's really new here, right? Okay? I didn't grade the quiz, so I put something on here to get you thinking. All right? All right. To do this, we have a complex alkene. We're going to end up with a product that has 2 chiral carbons. When we do these, and we'll do more after this, I recommend turning the alkene first. Here's the alkene. It's actually the same alkene we drew. Not exactly the same. Not exactly the same. Here's the alkene. Boop, 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 boop. There it is on the board. Imagine if I turned it. Look at this isopropyl. When I turn it, does it come towards you or go away from you? I'm going to turn it flat. The isopropyl is now towards you, right? Compared to the alkene. What do these two groups do when I turn it flat?
Go away.
You look at it, they're away from you compared to the alkene. Yeah. Just do that. And that's what I did here. These two groups are now back. This is just a different view of the starting material. But now we already have some good stereochemistry that's going to serve us at the end. And all we did was turn it. Now, what's the mechanism? Bromonium ion. Now you can do, I'm not doing full arrow mechanism here, but what happens? The alkene attacks bromine, but it's on a face, either straight up or straight down, either way. Then the bromine is up here. Attacks bromine, then what does the bromine immediately do at the same exact time? Backbone. And so you get a three-membered ring straight up. Straight up. That's why these bonds are straight up, not back or forward. Now you could also show this straight down. That would be the enantiomer. I'm just going with one here. Now what happens? Then the water comes in. Which carbon does the water attack?
The one on the right.
The one on the right, the same place the cation would have been if we had formed a cation. How does it come in? If the bromine is straight up, how does the water come in?
The bottom.
The bromine is straight up, how does the water come in? Does it come in from the back? The front? It comes in straight up from the bottom. So the new bond to the water, I'm going to lose a proton eventually, I'm not doing full mechanism, is straight down. The bromine just gets kicked off and it's straight up. See, it used to be bonded here. And there's your product. And your stereochemistry is already there. Plus an enantiomer, because you could have just the opposite. Put this in a Fisher projection. I put the isopropyls at the bottom in all the answers, so I put the isopropyl at the bottom. So this is going to be the bottom. I moved up here, and I drew it. Okay, you can do this one. I drew it like this, then I rotated it, and ended up like this, and there's your answer. And the bromine and the OH are on the same side once you draw these at top and bottom. Because we rotated it some. And this one is the fourth one. Now you may have gone through this process, and what you had here would have been the enantiomer. Bromine and OH would have been on the left. And you look at it and you say, well, none of them have the bromine and OH on the left. Well, yes, it does. The one that has the bromine and OH on the left is which one? It's right there. Enantiomer. So maybe that's what you end up drawing. You have to see that, you know. Because guess what? You're going to get both of these. Every reaction we're doing, you get enantiomers when possible. You only get this one, which was erythro. We'll add some good information here. That's erythro, this is 3O. Right? Okay. So let me ask you this here. New information. Question. Is this reaction here let's start with basic review. Is this reaction regioselective?
Yes.
Yes.
Why? Because the OH only ends up bonded to this carbon bonded to the isopropyl. You do not get product with the OH on the other alkene carbon. So not that region, but this region. That's called regioselective. Yes, it's regioselective. Okay. Is the reaction stereoselective? We need to be careful because there's two types of stereochemistry. There's enantiomers and diastereomers. So asking if it's stereoselective is sort of a, you need to ask, that's not a good question. You need to ask for clarification. Sometimes it may be if there's only one possibility. Here we got two possibilities. So let me get more specific. Is this reaction enantioselective? Do we only get one enantiomer and not the other? No, all of them. Like I said, every reaction we've done is never going to be an antioselective. Okay? An antioselective. No. Let me ask you this. Is this reaction diastereoselective? That is, do we get one diastereomer and not another? Yes.
I just don't understand
What do we get? We only get erythro. Do we get any trio? No. These are diastereomers of each other. Diastereoselective? Yes. It's diastereoselective due to the mechanism. It's also regioselective due to the mechanism. It's also not an antioselective due to the mechanism. Guess what? Everything's based on mechanism. It's not an antioselective because the bromine can attack from the top or the bottom, or whatever. What we got? Bromine. And so you start getting both, and that ends up to mirror images and enantiomers. Okay? So I covered this here instead of in the handout a little bit. We did that here because it was a reaction that included this. Does this make sense? Questions?
So is
Diastereoselective? Yes, check. Questions?
I have one about number 3. Could you tell us refill the sugar restriction with that one?
Number 3?
Yeah.
If you just put the F here and the OH there, you would have erythro. Why do you have to?
I wasn't sure if you had to rotate the whole thing or if
Well, if you just rotate it, you're not making the comment.
right. So if you rotate and you have to move the left over.
Right. I mean, you can't just move the F over there,
Right.
but also, because if you move the F over there, if you rotate it by moving the F over there, where's the methyl going to be? I mean, you put the F here, the methyl moves here. Put the F here, the methyl is going to be here. So if you rotate it with the F there, the methyl will be here. Then you would have, you'd have the OH at the top. Now, erythro and 3O has some vagueness to it, because if you could put the OH here, you don't do this, OH here, F here, and methyl here, that's just rotating, so it's the same compound. And you can say, look, they're both on the same side, it's erythro. Well, it can't be both. No, it's because of convention. Also, usually you want alkyls at the top and bottom. But it's also because I told you to do it. And okay, there is some ambiguity with erythro and 3O. That's why it's actually been, IUPAC has dismissed it. And, there's new stuff now that's more specific. That's why I usually tell you exactly how to draw it and then tell me if it's erythro or 3O. With methyl at top, F on the bottom, it is 3O.
Dr. Stevens, just to clarify, the bottom one we're saying is diastereomet or selective, and that means if we had this reaction, technically we could say there's 4 possible stereoisomers, but in actuality we're only going to get the 2 enantiomers, correct?
Right. In that
Okay.
reaction, the product has 4 different ways you could show stereoisomers, but you only get 2.
Okay.
That reaction only produces 2
Because of the mechanism.
because of the mechanism. Kind of sounds like the lab you did this week.
I get it. Yeah, because
The L for meso. See, the meso was not actually 2 because it's the mirror image is the same thing.
So here.
I have a question.
Question.
For number 3, what would be wrong if you drew the little men on the top left, on the top right instead of the bottom? Like if you started with the little men on the
I don't know. Did you get the right answer?
my F and OH were just on different sides.
you had the enantiomer, and that's not correct. You didn't draw that compound. You drew it's like if I asked you to draw this on the board, and you drew a left hand. I'm like, why did you draw a left hand? I asked you to draw the right hand. Did you not recognize, wanted you to draw the right hand? It's kind of like that. You drew the left hand instead. So it sounds like your little man or woman was in the wrong position. How did you have your little?
I just had him in the top right.
Up here, looking at what? What was going away from you? Because I mean, if you're up here, you're thinking the plane is coming towards you. I mean, the mouth was coming towards you. With the mouth coming towards you, you said the OH was on the left? Well, that's right. That's correct. But here, the mouth was going away. Hold on. The mouth coming towards me, OH on the left. That's actually correct. But the mouth coming, because if I was behind the hall, if the mouth would be coming towards me if I was back there, and the OH would be on the left. So how did you get it wrong?
I mean, because I drew the OH on my left instead of my right.
No, I don't know. We'd have to look at it. Because if you said the mouth was coming towards you, you put the OH on the right?
No, I put it on the left.
Yeah, but you drew it like this.
Yeah. I guess.
But you drew it as if the mouth was going away from you.
Yeah.
But you looked at it with the mouth coming towards you.
Mm-hmm.
That's where you messed up.
Yeah.
Question?
In the Fisher projections, how do you determine which group you're going to look at for erythro and brio, like between the F and the OH?
It's just like you do EZ nomenclature. It's isotonic number. Then you do tides. Okay? EZ nomenclature? I'm not confident that y'all are up on EZ nomenclature. It's the same way as you do EZ nomenclature. Okay. Here we go. I'll pass back the SciFinder assignment a little bit later. I've got to report the grades. Hopefully get them recorded. Okay. We'll maybe make comments about that at some point. The quiz, that will be posted upstairs, quiz key. All right. Okay, let's all of our handouts. We'll go through and we'll see what we left out. All of them. Alkynes. Stereochemistry warm up. Let's maybe start there. I sent out some answer keys yesterday. Yeah? Email. Maybe let's end with this. Let's do some of the others first. Thermodynamics we need to do. I want to get a video. We'll see a video of that. Halftime. Okay. Let's start maybe at the beginning. Intro to alkenes. I believe you printed out that yourself. Maybe no. Not sure. That included the EZ nomenclature. Questions about EZ nomenclature? questions? Also, on the video, did I do the ones at the bottom here? Did we do these?
You're on the, he's on the easy.
Did those?
As in if you spot names or the Z
Oh.
E or Z? Was this E or Z? Z? Okay, any questions on what was this one?
Z.
Is the same size?
It's the same thing.
And E stands for opposite. Opposite size, like they're both vowels. Okay, what was this one?
Z.
They were both Z. Okay, any questions about those? Understand why those were both Z?
We only look at the highest priority group on the left and right side, we don't compare it from like top and bottom.
What do you mean
Like
size?
we look to compare.
We look at what's the highest priority group on this carbon? This one or this one? Well, they're both carbon, so you got to look at what's attached to it. What's attached to this carbon? A carbon, and an H. What's attached to this carbon? A carbon, H, and an H. This carbon had, hold on, no. What's attached to this carbon? Carbon, an H, and an H. What's attached to this carbon? Two carbons and an H. That's what's attached. No winner here. Here's your winner. Boom. So this is your high priority group on this carbon. Over here, which wins? O or S? S. High priority groups are on the same side. That's different from this side, that side. It's the same side of like cis trans. Like the high priority groups are cis. That's what it means, the same side. Cis or trans. And when the high priority groups are cis, we call that C. Okay? It's called Z. It's more specific. Otherwise, you say, hey, that compound is trans. Or what do you mean? I mean, when the high priority groups are on the same side, it's cis. And instead of having to say all that, that's what that right there means. High priority groups are on the same side. High priority groups are cis. That's what Z means. Other questions about nomenclature and the EZ terminology? Okay, let's look at anything else in this handout. Don't think so. It was just some miscellaneous stuff. In the back it's talking about refrigerants, fluorocarbon, freon, those type of things. Some of those tend to be alkenes. If you look at this nomenclature, if you're asked to name this compound, would you have named it this way? Okay. Tom, why didn't they say cis or trans or E or Z for this guy?
Because it's
I
not.
mean, they did down here, but why not for that
It's
one?
not.
There's no cis or trans possible. That alkene's not stereogenic. I mean, can you have both an E and Z? No, it's not needed. It's not. So that alkene's not stereogenic. Everybody go with stereogenic alkenes? These are both stereogenic, so you have to have a stereochemical descriptor. They're both trans. Now with two groups, trans is fine, it works. Or they could have called this what? They could have called it E, because that means the same thing, but you can also use trans for two groups. When you get more than two groups, you need to start using E or Z. Okay? All right? Hey, I give you these for the interest, but you can also create quiz tests. Okay? Let's see, would I get the same name? Well, there you go, did you? There's some practice. Hopefully you would get similar names, and so in the context of this article, you can see how they use some nomenclature. That's that. Then we went to, we'll do thermodynamics at some point. Addition to the big handout, all of our reactions. Let's look there. Back at the second page, I know we left one off. At the bottom here. Did anybody get an answer to this one?
Yeah.
So the one on the left.
Then with the oxygen, with the,
Anybody say the one on the right?
no, I mean, I put the one with the ether.
Do what?
I put it with the ether.
So the one on the right?
The run up, yes, the one on the right.
Okay. The one on the right is the major product here. Okay? Two different cations they can form. I say top or bottom, well let's show top or bottom. If the cation formed on the top, it would be this, and the new H is here. If the cation formed on the bottom, it would be this, and the new H is up here. Your two cations. Question is, which is more stable? Well, this is tertiary. All right, this is all connected. What is this officially down here? Primary, secondary, what? No, officially secondary. How many carbons is this bonded to? Two, secondary. So you might say tertiary is better than secondary. But what we have going on here is, yes, resonance. And resonance often is more important than just primary, secondary, tertiary. Resonance is, on day one, we would have said this carbon needs bond. And if we can get it some bond, it makes it better. Well, next door has lone pair. What if this lone pair comes in here and starts sharing and makes bond? What does that give? All we're doing is moving pi electrons. Because one of these lone pairs is in a p orbital. Why? Because there's a p orbital next door. And if we make bond here, one lone pair left, positive charge there, we can show an alternative Lewis structure, which is called a resonance structure. What we have done here is, the true structure is somewhere in between. When you start doing resonance, true structure is in between. We now have red and white, and I have to explain that the true structure is pink. The true structure looks like a blend. That is, it's not a single bond between here, not a double, but somewhere in between. It's like a bond and a half. What about charge? Carbon doesn't have a positive. There it's neutral. The true charge is somewhere in between. What's in between? Partial plus, like a half. So we're going to say, again, this looks a little disconnected. I'll never get it right. Partial plus. What's the charge on the oxygen? Not neutral, not positive, but partial plus. If you could look at this intermediate, it would look like this. That is, you would have some bonding between them. I mean, why not? Electrons attracted to positive. This is the idea of delocalized bonding resonance. But here's the take home. What has it done for us? Here, the carbon is full positive. That positive has not moved anywhere. Here, is this carbon full positive? Well, you got to be careful. This is really not the correct representation. Is it full positive? It's only partial positive. Some of the charge has been delocalized onto the oxygen by resonance, and this is a powerful effect. It makes the system better. You're spreading the charge out by resonance. Okay? This is actually the better cation. A resonance stabilized cation is typically going to be better. There may be some cases where it's not good. Okay? And because of that, this is where you get the cation. And so then the bromine in the fast step attacks here, makes bond, and so you get here. Now you can work with any resonance structure. We could have come in here and attacked here and move the electrons over to there. That gives the same thing. You will not attack the oxygen because oxygen doesn't want 3 bonds. It wants its lone pair back. So you push the lone pair back, or you just attack over here. This is somewhat analogous to bag bonding. Is it really a cation? Well, it's a hybrid. We don't call this bag bonding because when you make pi bonds, that's resonance. But it's sort of analogous. And attacking here, moving that over, is sort of like backside attack. But these are resonance structures. We'll cover resonance for test 3. But you can't avoid it. Now a lot of books cover resonance on test 1. Okay? I think it's too much to give you everything on the first couple of days. I just sort of eases into it. Okay? So, the answer is really one on the right. Questions about this? Does it make sense at all what we're doing here? Resonance is hugely important. Once we cover it, you'll use it a lot through organic too. Like hydrogen bonding is often the answer for IMF stuff. Resonance is often the answer for lots of reaction outcomes. What else was here? I think we did, tell me if I missed something, but I think we did everything there. Ring expansions, did we do that mechanism?
No.
One at the bottom?
We didn't go over it.
Yeah, I think we did the one at the top. How we do on this? Well, this is a ring contraction, obviously. 7 went to 6. The only reactivity we have is alkene. Alkanes are pretty unreactive. They don't have a lone pair or a reactive pi bond. Okay, we're going to make cation, top or bottom. Maybe because you see where we're headed. But they're both going to be secondary. Maybe you can do one and then you're like, oh, I'm going down the wrong road and maybe I have to consider the other here. But now usually I'll tell you, okay, we want it one step at a time. You can sort of think backwards a little bit over here before you get going. For example, does everybody agree that I probably at some point need that cation? If I can get to that cation, what would attack it? Water. Okay? So that's something good to recognize. But we don't just go there directly because you'll like, I don't know how to get there. One step at a time. The only reactivity, now also, we kind of got a cation up here where you got this dimethyl. So it's almost like somehow we want to get a, so this is what I would probably see from this. Probably let's make the first cation there so we can easily rearrange and get it there. So H plus water, right? That's what that is. Electrons pull down. I think that's 7. Electrons pull down to make bond to H, leaving that as a cation. One step at a time. That's reasonable. Now let's think about a second step. We get a cation here with these two methyls. If a methyl moves over, that ain't going to get us that. We're going to have methyls on 2 different carbons.
I said that bond.
This bond moves over. Now it might look like it can't make it over there. Like, how is this going to disconnect? But this is a big ring, and it's got bond angles. And I'm not drawing it all right, because maybe this is like this. But if we disconnect this and reconnect over here, disconnect and connect here, what would that give? Well, I'm going to draw it as if I just did that. Boom, 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 boom. This used to be here. I pulled it away and made it bond there, 2 electrons. So now it's bonded there. You see? Like a windshield wiper. There you go. Well, what's here now that we need to draw?
Cation.
Cation, because it lost a bond. What size ring do we have now?
6.
6. It's ugly, but it's 6.
It's gonna rearrange and go
Well, that's not actually a rearrangement.
I mean, it's gonna fix it.
It's just a redraw. That's the same thing over there. Just redrawn nicer and there you go. This was an alkyl shift. This carbon, instead of bonded there, is now bonded here. It's an alkyl shift, but it's part of a ring. We actually contracted the ring. Why did we contract it? Well, we went from secondary to what?
Tertiary.
Tertiary. What's another reason we contracted it?
The size of the ring.
Size of the ring. 5 and 6 are best. We went from a larger, too large, to a nicer 6. Better bond angles. Here, what's next?
Water.
And now you're home free, yeah? Boom. These electrons attack cation. Oxygen. A lot of you want to just lose an H by magic. We're not doing any magic here. It just doesn't disappear. Bond makes, this is it. Those 2 electrons are now bonded to that carbon.
Then another water.
Now we need to get, hold on now, that's a plus charge. Don't forget charges. Why is it plus? Because look, if a plus reacts with a neutral, you still have a plus. The plus is not just going to disappear, the plus is now here. Now you come in here with something, water, there's also a minus here that you could use, but it's not given. It's given generically. Water can come in here, bond to the H. These electrons move on to the oxygen to give it second lone pair, and you reform the acid. The H plus. You reform water in H plus, but H plus never sits alone. It's always with something. You reform the acid catalyst. There we go.
When we
Yeah.
ask for a mechanism like this, right, and when we finish, we get the product. But what if we don't show the reformed acid or whatever in our answer when we do our mechanism? Is that okay?
It's okay. I mean, I asked you to show formation of that.
Right.
I didn't, in directions, it doesn't say show, it might, but no. I mean, I usually do it just to reinforce, hey, we reformed the catalyst. I'm just being, okay. How we do? How about a little THC? Never did this one. How we doing this one? In fact, somebody confident you got it? Good. See what's going on here? Acid catalyst. It's actually going to be a catalyst. Well, let's just assess first. What do we need to do? We need to make this 6-membered ring over here.
With an ether.
And it looks like the oxygen is now bonded to one of these carbons.
Break the alkene and use an H off the O.
We've predominantly been doing pi bond chemistry. I mean, you got an alkene here. I mean, neon sign, alkene. Now you also have an alkene there. Do we want to react that one? No. Why didn't it react? Well, ask Mother Nature. But now, where are we going to make cation when this attacks H+? Left or right?
Left.
Correct. So this pulls away this way and attacks, and that gives. Now I'm going to draw it a little abbreviated. Usually I don't give you such a big structure on a quiz, so you don't want to spend all the time just redrawing structure. That's. But we got boom, boom, new H here, cation here. This goes here to the ring, and there's an OH here. Okay? and the rest there. This is the business part. Okay? Now, do you see any way for this to make bond here? Yeah, these electrons then add here. Just like we did with water adding to that cation. It's an internal nucleophile. It's not water, but it's a lone pair of oxygen. What is that going to give?
The oxygen.
Well, I lost the number of carbons here, but if oxygen bonds here, right? What size ring? 1, 2, 3, 4, 5, 6. That's the 6-membered ring. So that comes in here. It's a carbon with 2 methyls. See, this looks odd. It looks like it's 2 methyls now. Carbon with 2 methyls. The oxygen is now bonded to it, but we didn't lose the H. And this is bonded to this ring. And this is here. That's a 6-membered ring now.
Positive charge.
Positive charge. New H is here, but I didn't draw it in. Then what do we need to do?
Attack it with water.
See the one on the right? Same thing. Some type of, this is in the plant. So when you water your plants, or it rains, this plant has water around, yes. Okay?
My marijuana plants that
Uh-huh.
Yeah,
Here. Yeah, make sure you water your plants, okay? Water's important.
next to my kale.
All right. What is this? There you go. All right. Who sees this? Maybe after a few days, a week of doing mechanisms. Yeah. If we had did this earlier in the week, it may have. Hopefully, you now see it a little bit better. Yeah. How do you describe this? It's cation formation and then intramolecular attack of a nucleophile. The nucleophile is intramolecular, it's already there. As opposed to intermolecular, where we brought in some external nucleophile. And usually when you make rings, probably always, you attack internally. And okay? Cyclization. There you go. Tetrahydro, it sounds like 4 hydrogens compared to this. Probably, if you look this up, it's going to have pi bonds in there where H has been removed. I don't know, but THC is sort of the more important one. Cannabidol, is that a diol? Actually, no, it's not. That's odd. It's still being called a cannabidol. No, it's not a diol. The O is not there.
Cannabidol.
Okay, see, this is diol, 2 O's. Yeah, but now I didn't notice that. I would go to, okay, cannabidol, because there's only 1 alcohol now. The other one is a what? That's now an ether. Okay, I would have been calling it tetrahydrocannabidiol. It's not a diol. Okay, what was next? I think epoxides. Oxide. Did we do down the bottom? Did we do the first one?
You did the MCPD.
Yeah, and we used dichloromethane as solvent. Have you ever used dichloromethane as a solvent in a reaction?
Yeah.
Sweet? Yeah. It's a common reaction solvent. Okay. We did that one though?
Yeah, you did the top.
Okay. Here. This is a kind of a condensed for a peroxy acid. Alkenes peroxy acid, what does that give? Epoxide. You've got to know that when you're not just looking at this page. Alkenes and peroxy acids. That's epoxides. Epoxide. Okay, now our information mechanisms kick in. If we don't do any stereochemistry, we make epoxide and we got a methyl in. But we have stereochemistry. Because now these 2 carbons are tetrahedral. We can make the rings of the ring, the bonds of the ring in the plane. What about the bonds to the oxygen? Are they going to be cis or trans?
Cis.
Got to be cis. Got to be cis. You can't have a three-member ring trans. But they're also cis because of the mechanism. The alkene attacks the oxygen, and what does the oxygen do? Bag bonds. Both bonds are on the same side. Since this is bolded, this is by default what? Dash. Now we have stereochemistry. But question, is that the only product, only structure to draw? Ah, plus an enantiomer. Why? Does this compound have an enantiomer?
It can also be dashed to the concept.
Hold on. Is this compound chiral? Where's Waldo? Waldo's not present. There's no planar symmetry. So yes, it is chiral. That means the mirror image will be different. Yes, it does have an enantiomer. Will you get the enantiomer? Yes, every reaction we've done is you get the enantiomer when possible. None of them have been enantioselected. How do you get the enantiomer? Instead of the chemistry taking place from the top, it takes place from the bottom. Or instead of it taking place from the front, it takes place from the back. If it takes place from the back, it will look like this.
No.
And there's the enantiomer.
So,
How do we know it's the enantiomer? Well, everything's been switched. We switched all projections. Now, if you want to show it mirrored, flip this around. If you flip this around, the epoxide will now look like this. Now you see how they're mirrored. But these are the same. We know we can get the enantiomer by just switching projections. You'll get them both. Okay? Now it's easier to show stereochemistry with rings because you do not have free rotation. What about the next one? Peroxy acid, alkene, we're going to make an epoxide. Three-member ring here involving these two carbons. Somebody have a product here?
yeah.
You don't have any stereochemistry yet.
Yeah.
Because your product has two chiral carbons.
Yeah, right here, I just didn't do the dash line.
Okay. If we don't do any stereochemistry, it's going to be like that, right? Oxygen. Yeah, but look, we have two chiral carbons. How many possible stereoisomers to show? 4. Are we going to get all 4?
Yes, you
Do it?
are. Yes, you are.
I can't.
Yes, you are.
You're going to get all 4.
You're only gonna get 2.
No, you're only going to get 2.
It's only back line.
Oh, okay.
Because of the 4, 2 of them would have to be where the bonds to oxygen are opposite.
Oh, okay.
You're not going to get that. Mechanism does not give those. Okay?
So we put the dashes for the hydrogens or for the carbon bonds? For the hydrogens.
You could do either, because if you make one dash, well, typically, yeah, you could do either. Because if you make one dash, that implies that the other one's full. Okay, here's how I would do it. This is one of those where I would rotate this. Our product has 2 chiral carbons. I would rotate this. That is, before we do anything, let's draw it like, this is trans, right? We can draw the methyl coming forward and the ethyl going like this. Now we've made it where the alkene is flat and we have up or down. Okay, here's the alkene. It attacks the oxygen, kicks off the other one, and then that oxygen back bonds, same exact time. So the two bonds would be straight up. We'll get rid of this and draw the two bonds straight up. But we could have also done it like this. What's the other way we could have done it? Get rid of this and draw the two bonds straight down. Now this kind of looks like an ugly bond angle. If you want to, it's still forward. If you want to kind of make it like this and make it look a little bit better, bond angle, it's fine.
Would like drawing it like this be? Having a.
You chose to put the new things forward or back.
Mhm.
I'm always going to put the new things in the plane, up or down.
So would that be?
And you see how these are mirroring each other? Yeah. That plus an antonym. Okay. Will you ever get the one where to get the opposite you have to draw this down and this up? You're never going to get that. That is, if you determine RS here, this is oxygen 1, carbon, this is R, and this is oxygen 1, carbon with oxygen is 2, ethyl 3, H4, R. So this should be SS. You will never get SR or RS. That would imply that would have to have the two bonds to oxygen opposite. You will never get that. So you get this. That could be a sufficient answer. This plus an answer. Then a question could be asked. Will the groups on your epoxide be cis or trans?
The groups on our epoxide
Trans.
trans.
Here's a ring, 1 dash 1 bold and trans. Can you tell that from your drawing? It's not as easy, is it? No. This is the way I suggest. You only learn this today. Turn your alkenes when your product ends up with, all right? Down below. It's really a repeat. Do that one. What is this? That's just a specific type of peroxy acid, yeah? Somebody have it? I'm going to turn this first. These groups are cis, so I can draw them both. Hold on. They're cis. Right? How did you get that? If I turn it, won't they, like this, right? I mean, if they're both coming forward, right? I mean, boom, boom. They're down like this. Watch the fill on the ethyl. Now they're coming both towards you. I could have also turned it that way and they'd be both going back. I could have did them both dashed. Now, when you get the epoxide, what do? How did you end up with these being trans on your epoxide?
Because I wrote groups on epoxide for trans, because I thought you said that on the last one, so I just on that was only that example.
That was only that example. No, I don't know. One thing that is certainly is the two bonds to the oxygen are on the same side. They have to be. I can't make a three-member ring.
Yeah.
No. No, it's that plus what? Is this compound chiral?
Yes.
Yeah, there's no point of symmetry there. Plus an antimer. Now here's a mistake that some of you may make at some point. You'll say this plus an antimer, but the compound won't be chiral, and so there is no enantiomer. So I will say, well, why did you say this? But yes, this one does have an enantiomer. What's the enantiomer going to look like?
Dashed.
Two ways you could show it. You could show it like this, but make these like that. That would come from just turning the alkene, well, instead of the, well, it's turned back, and then it comes in, okay? But we could have also showed the enantiomer another way. We could have showed the enantiomer starting with the same thing, and instead of drawing the bonds to the oxygen up, we could have drawn them down. That would have been the enantiomer. The bond angles are kind of bad. It'd be better to have these going a little bit up. They're still going to be forward. Forward. And here's the enantiomer.
No, it's the same.
These two are the same. These are enantiomers. There's the enantiomer.
Yeah.
Those two up there are the same. Just flip it. You flip this over. Okay? If the groups are coming back, and I flip it over, now the groups are going to be coming forward. That's all I've done there. What's an enantiomer? Okay. Now, can you do this here? Sometimes, some books will show you this, and the product is going to be, that is, I'm just going to erase the pi bond and put it in oxygen. Well, how do you want to put it in? Well, bolded. Or
That's what I did.
you could do that. Problem is, I'm not going to do it that way. I'm going to do it the way I'm doing it. I'm turning it first. And we don't have time for me to show you every single way because it's, what about the third and fourth way? I'm showing the way that I recommend. I recommend turning this first. Sometimes out of there is going to get you in trouble if you don't know everything. Yes?
Is that an acceptable answer though? If you understand this is in trans, what's going on?
Certainly, because I never ask you to draw it. I usually say draw right hand. If you draw the right hand with the thumb over here, I can't say, sorry, you drew it. If you draw the right hand, I have to accept it. The question is, which one is this? Which one down here is this?
The one on the right?
The problem is you can't tell if it's cis or trans.
Yeah, but the,
Well, yes, but.
We have to assume that the H is back. I think I can say they're cis because
Like for that one, but for the
oh,
second
so
one.
to
that
the
we did,
right.
We couldn't tell which, if it was trans.
this one here.
I mean, yes, for this last example, but for the second one.
No, I think it's trans.
Yes, for this one, the way if you draw it like that, you can't tell which one's forward and which one's back. If you draw it like that.
Draw like this.
If you draw it with, like the way I did the first time, I couldn't tell which group was forward and which one was back.
Okay, I'm not sure. But this one, which one is it? The way I would have to tell is do RS. Do RS. Let's do RS real quick here.
It doesn't.
Carbon with oxygen's 1. Let's draw this phenyl out. This might be good practice. Phenyl, benzene ring. Carbon or carbon? Well, what's this carbon bonded to? That carbon's bonded to a carbon, carbon, and H. Carbon, carbon, and H. What's this carbon bonded to? This is good practice here, because this may have not... What's this carbon bonded to? Carbon, carbon, and carbon. Why? Because when it's double bonded, it's kind of as if it's bonding to 2 carbons. No winner, no winner, winner. This is your winner. So this is 2, this is 3. We're looking at what's connected here. 1, 2, 3. H is in the back, so this is what? R. How about the one over here? Oxygen's 1. Carbon, they're both carbons. This carbon is bonded to what? An oxygen. It's bonded to oxygen, carbon, and H. Yes, this carbon bonded to oxygen, carbon, oxygen, carbon, oxygen, carbon, and H. What's this carbon bonded to?
Oxygen.
Hold on, where are we at? We're determining this carbon. 1, 2, what's this carbon bonded to?
Carbon and 2 H's.
Carbon, H, and H. Which wins? O beats carbon. That's listed in the highest. So O beats carbon. So
That's 2.
this is 1, this is 2. No. Oxygen's 1, carbon with oxygen's 2, 3. Look at here. 2.
So it's
1, 2, 3. R, H in the back. Yeah, they're both R. You have to find which one is RR here. Whichever one is RR here is the same thing. That's how I would do it. Or you can make models and see which one looks the same. One of these down here is RR, and I'll let you do that on your own. Question?
The bottom row, there's not supposed to be 2 phenols on the middle. Is that right or no?
Of course. This is supposed to be just an ethyl. Right? Question?
So you can draw it like the top two, and then figure out which one.
Whatever works for you. I did it by turning. I got these. There you go. If you want to do it another way, you're welcome to it. There's probably a half dozen ways. I can't present every single one to you. Some of you don't want to hear the other one. You just want to be able to get it right using one method. Okay. Cyclopropanes. Did we do products at the end of that page? Did we do both at the bottom there? Sounds like we did. Next.
But that first one at the bottom, we need to do the whole switcheroo thing, right?
We didn't do.
Sorry.
Which one did we not do?
Well, I think we,
The phenol.
the one with the phenyl there, do we need to, when I look at that, I need to do the,
Oh, did we do the bottom? We did this one down here?
Yes.
Probably because rings are easier. I did that one. I said we'll probably let you do that one.
Yeah, we didn't do that.
Okay. Again, that's one where I would sort of turn. What are we making here? This is simple carbene. We get the CH2 carbene, right? Got a lone pair that's got dual reactivity. It's plus and minus. This attacks the cation part, but at the same time this back bonds. Cyclopropane, no intermediate. How would I do this? You're going to have 2 carbons here. I would turn this. They're trans here. Let's put one forward. and let's put one back. Do it like this. That's ethyl, right? Is that it just turned?
Yeah.
And so we turn it like this.
So it doesn't matter how we turn it.
Doesn't matter. There's two ways. You may end up with an enantiomer, but we're going to get the enantiomer anyway. What's the outcome here? We get rid of the pi bond, right? And there you go. You make your cyclopropane. Here's the pi bond. The carbene is down here. Pi bond attacks carbon. At the same time, the lone pair back bonds. And you make three-membered rings straight down. Three-membered rings straight down. There's the product. But that compound's chiral, so you're also going to get what, most likely?
The enantiomer, which is.
Enantiomer. What would the enantiomer look like?
Draw the same.
You can draw the same with the carbon bonding from the top.
Yeah.
Yep.
Now, if you were asked, are the groups on this ring, it's a small ring, but it's a ring, are the groups cis or trans?
Trans.
Groups of trans on that ring. Again, that's kind of an ugly bond angle. If you drew it fresh, I would kind of draw this a little bit up, maybe bolded, but that's acceptable. You don't want to get too ugly bond angles. Is there anything else in this handout? I think that was it. Miscellaneous applications, steroids. Okay. Summary of alkyne reactions. Anything in the alkyne handout? I think we covered it all. Questions about alkyne? How was the alkene able to learn all its electrophilic reactions? Because of olefin. Olefin is just an old slang name for alkene.
Oh, I had asked you to go over number 17.
Yes, let's look at that. 17. Number 17. I usually cover this at the very end of the course when we do radical reactions. But I can mention it now because it's fresh. If the peroxides wasn't there, where would the bromine end up? Left or right?
No, right. Right.
Right.
Yeah.
As in incorrect.
Yeah.
This attacks H, leaving cation there, and bromine attacks cation.
Yeah.
Okay? Whenever you include peroxides with HBr, you get the reverse regiochemistry. There's your statement. So with peroxides, now when the bromine ends up here where the cation would be, we call that the Markovnikov product. Because the nucleophile ends up where the cation would be. If the nucleophile ends up over here, it's like, how did it end up over there? That's called the anti-Markovnikov. Peroxides gives you the anti-Markovnikov. We'll look at the mechanism a little bit later. Maybe or maybe we won't. Maybe this is just something to just sort of make a statement about. The addition of peroxides to HBr gives the opposite outcome. So on the flip side, which product is the opposite outcome? Which product is that?
T.
T. T.
T. T as in tornado. Yes, new H here. Bromine here. Yes. Why are they saying 4 stereoisomers?
Just 2 chiral.
Because you got 2 chiral carbons. Are you going to get all 4? Apparently you do, according to them. Yeah, you get all four. If we look at the mechanism, you'll see there's no like backside, there's no restricted attack. It's all going to be random. You end up with all four. Why did they say for this one plus an enantiomer, but for this one no plus an enantiomer? That's not a good question unless he's. No, it is. Yeah. Why didn't they say plus an enantiomer here?
There's no chiral carbon.
Compound doesn't have an enantiomer. It's not chiral. Okay, hopefully that was useful. Yay, nay? Good practice there. Okay, let's see if we can finish up here. Yeah.
Are you going to go over the thermodynamics?
Thermodynamics?
Yeah, just a warm-up.
I don't know. I asked on Tuesday, and you all didn't have any questions, and we sort of just kept going. Do you have questions about thermodynamics?
No, I just want to see the answers.
You just want the answer?
Yeah, I mean, I did it.
What questions do you have? Just want to check your answer?
Yeah, I wanted to make sure I did it.
Like which question?
Number 1, 2, 3.
Which reaction gives off the most heat? That's just from your calculations. Which one was that?
I just want to make sure I was using the right
Okay.
I did my math.
Maybe I'll send that out by email. I'd rather cover this here. Okay? We did some of these, Fisher projection. Did you want to do any of these up here? Was this RS? Did someone get it? I see S. If I get S, got a 50% chance. Okay. I'm looking at the low priority group is the H.
Yeah.
We want to look at it, but it's not going back or forward, so we can't just like maybe switch it. I'm going to stand over here and look through here. With the H going away, can we draw that so we don't have to just keep it in our mind? Yeah, we can draw it like this because that's a chiral carbon. F at the top, F is going straight up, and the H is coming straight down in the plane. If that's the case, the bromine is on coming towards you guys. Bromine's on the left, and the SH is over here. Now let's clear our mind. Okay. Now I don't have to get all jumbled. Now I have to look at it like this. What's 1? Bromine. What's 2? SH, correct? Or S. We're not worried about the H. It's the S. Is that right?
Yeah.
Okay, how's the H now? The bottom, so it's going away. So the low priority group away, what is it? Counterclockwise. S. Sinister. It's rotating left. Is that why the left eye is called OS? Now the right eye is not called OR, it's called OD. That's from DL. And they use a capital D, which is not the same as chemistry, but what's the direction here? LIBO is left, so D is right. D rotates to the right. So when you see OD, that's the right eye. I think that comes from that. Ocular D and ocular S. Anybody in ophthalmology? Okay, so free information. It's applied to some of the terms we're using. Okay, anything up top? If not, how might you separate this compound? How might you separate the enantiomers of that compound? We're ever separated enantiomers? That's on the back of the handout. Let's look at that. Do enantiomers have different boiling points?
Yes. No.
They have the same exact physical properties. So you can't separate them by distillation. How does that separate? Keep thinking, maybe you can come up with some experimental design where you use that to separate them, but I don't know that it exists right yet. Just use that to your advantage to separate? I don't know. Here's a way to separate enantiomers. Using a chiral resolving agent. Okay? And acid-base chemistry. Acid-base chemistry. If we have an RS mix of enantiomers, and we do a reaction, if we react this mixture with S, something that's this S, now how does that separate? Well, that's, where did it all begin? But if we have something that's just S, this mixture will react with S to give a mixture of RS and SS. Because the R molecules will react with S to give RS, and the S molecules will react with S to give SS, if they join together by a reaction. Now these are enantiomers of each other. But what is the relationship between the mix now? What's the relationship between RS and SS? Are those enantiomers? No, because the enantiomer of RS is SR. What's the relationship?
Diastereomers.
Those are diastereomers, and diastereomers have different properties. For example, in the lab, one had melting point of 250, and the other one was 150. Huge difference. They also have different solubilities, different boiling points if they're liquids. Now you can usually separate them. And the S is called a chiral resolving agent. These can be separated. In this example, they're separated by recrystallization. You have to read this. I'm not going to read every little bit to you. Here's a specific example. You have a mixture of this amine. Okay, R and S. Or D and L. They're calling it a plus-minus mixture. That means something, right? It's DL. You can react this with tartaric acid. Now this actually has two chiral carbons. But tartaric acid, I believe, is RR. Pretty sure here. Both of them are R. And so you end up with, this is a mixture, RRR and SRR. When these react by an acid-base reaction. These will react by acid-base because the amine is basic, and you've got this carboxylic acid. Reacts with one, and so you make an ion pair. Now, this isn't something we have to note. When we combined and made these up here, you may have assumed that this combined covalently. They can also combine ionically. That is, like down here. Now this is one thing. Here. It's two separate ions, but we're calling one thing. And this one is RRR, where the one below is SRR. Now both of these are solids, and actually this one will crystallize selectively and the other one will stay dissolved. Now, how do you know that? Well, that took research. It also depends on the right solid. This is an example of using the process. Then you get pure crystals of this. Then you can like basify this and you can take it back to this and it would be just pure enantiomer. You have to read that. I went through it quick. There's another example at the bottom. That's called using a chiral resolving agent. And you're making diastereomers. The diastereomers can be separated. Then you have to go back to the enantiomer. If you're doing acid-base reaction, you can go back the other way by just neutralizing it. Didn't you do that in the solubility lab? Made it acidic, and then you went the other way with base. Okay, that was quick there. I didn't get the cyclone to return to you or make comments about that. Do I? Yeah, we're pushing time here. Pushing time, I think push time going to a test on Monday. Is it okay if we delay the test till Tuesday?
Perfect for me.
Yeah,
Six is
Oh my God, I love it.
Friday you need to win, so I'm
Okay,
gonna
well, let's see, what you can't do is just take the weekend off. for example, and study.
No, Monday,
You gotta act like it's on Monday. On Monday, we will start new material, test 3 material. And if you'll please allow me to return the cipher under on Monday, because I didn't get the grades recorded. I did bring them. Recrystallization, okay, we'll turn that in. Thank you.